Thank you everyone thank you so much for starting out, and thank you for hosting me on this beautiful campus next to the water. It's been a really nice day and had loads of interesting conversations. Please shout out if anyone needs me to slow down or tell you something, or you have any questions, because that'll be good, because there's sometimes I'll just talk about things that are at the wrong level, specifically because in the room today we have at least two people who have thought about this topic a lot. And I've actually been giving this talk around the UK and the US, but it's the first time I've done it in front of people who have actually really studied this. So let me get the level right. All right, so anyway, I'm going to talk about work which I started as a postdoc at the British Antarctic Survey, and I have special thanks to my supervisor, who sadly passed away now, Richard Hindmarsh. A lot of this was his brainchild, and he's a great mentor. And of these two guys, Ian Rudkin and Scott Webb, some of the people in the field with me, where we collected some of the data we'll talk about. But I'm going to talk about 10 years of work that I've done and lots of others that have done since on this idea of the ice sheet, the Antarctic ice sheet, having retreated and then re-advanced. And in case I don't get to these takeaways, or I don't get them across clearly, these are my takeaways. The West Antarctic ice sheet re-advanced to its current size in the Holocene, but we don't know why. And the explanation for this has implications for the future of West Antarctica. Those are the things I want to kind of persuade you of today. So just as a little taster, this is what the West Antarctic ice sheet looks like when you're on the ground. It's, to the naked eye, exactly flat. There's nothing to see most of the time. You just have sky. And I was there with this guy, mountaineer called Ian Rudkin, who's also a really good photographer. And so what do you take photos of? There's just clouds, basically just clouds, and our field camp here. And so this is a time lapse of the clouds. We got those beautiful pictures of that, but honestly, there's nothing else to take photos of. But this will give a feel for the field work was like. This is our little pyramid tent, and the two of us slept in there. And then we've got science kit here and a couple of skidoos and sleds here. And that was our whole camp, which we moved around the ice sheet, taking measurements. And I'll show you how those kind of very small scale measurements really led on to this larger picture that we built up of what the ice sheet has done in the last few thousand years. Right, that's where I'm going to go. But I'll do a quick intro about why we care about all of this stuff. So as many in the room study, probably the sea level is rising, and this is a time series of global sea level change, and over a few decades. And this is a little bit out of date. It's a little bit of an older paper, but the reason I still use this slide is because they particularly focused on the fact that, of course, well, sea level is going up, but there's also, statistically, they managed to show there's a curvature to this, an acceleration of that sea level, and they were attributing trying to find the sources of that acceleration, and most of that acceleration is from the ice sheets, Greenland and Antarctica, starting to contribute to that mass to the oceans. So that's in millimeters, and then let's zoom in on Antarctica. We've got another time series here of the mass change of Antarctica, and just let's focus on just the purple, because that's the whole of Antarctica. And relative to some baseline in 1992, we've had this accumulative reduction in the mass of Antarctica, and that's in the thousands of gigatons. So gigatons, a cubic kilometer of water. And in a very simplistic way, that contributes millimeters to sea level rise. And this acceleration is what we're talking about as the cause of that acceleration of global sea level rise. Now, why do we care about this? This is on millimeter scales. Why do we care? Well, we have this concern or projection that this will continue and accelerate into the future. And this is from an IPCC report on the changing cryosphere. And this is now a time series going out from present day through to 2300. And these two curves correspond to projected sea level rise, mean sea level rise around the globe. And the two colors mean two different scenarios, red being the higher emissions. And really the main point is, I want to make here twofold. One is that the numbers here are much, much greater than we were talking about before. We're talking about millimeters, maybe 10 millimeters. But look at the scale here. This is in meters. It's very extreme. And you could argue about how good are we at predicting the future? Well, not very good in this case. And partially that inability to predict the future is represented here by these uncertainty bounds. And most of that uncertainty comes from the unknown poorly predicted behavior of the ice sheets. So that's we would be, overall we would like to be able to predict how the ice sheets are going to change, but it is really difficult to do this, right? And to put it really simply, it's because they're really hard to observe. For one thing, they're really huge, right? This is a system, like all of us in the room are used to this idea. If we study the oceans or the atmosphere, used to this idea that these systems are big. They are not phenomenal that you can fit in the lab and do experiments on for the most part. So this is the US, contiguous US over Antarctica. Simple, they're a very large system. And probably more importantly, they're very complicated. And this is a cartoon where a blob of ice here is left resting on the lithosphere and the ocean's lapping up against it and the atmosphere is interacting with it. And you won't see the details, but the arrows are all processes, maybe like heat fluxes or mass fluxes, interactions between these systems. You have the ocean providing heat to this floating section of the ice sheet. You have the mechanical load of the ice sheet flexing the lithosphere. So that's glacial isostatic adjustment. You have the atmosphere, of course, feeding the ice sheet with precipitation. And all these things are interacting in multiple complicated ways. So these are the reasons that it's really difficult to predict these things. All right, let's have a look at how these ice sheets behave. A lot of my research is about the ice sheet itself. And let's talk about how they operate very broadly. So this is a color map showing the velocity structure of the ice sheet. And the colors themselves mean the speed. So oranges are like 1 meter a year, roughly. And then the purples at the edges are maybe 1,000 meters a year. So overall, it's flowing slowly in the middle and accelerating out towards the edges. And these blue little lines moving out towards the edge show the direction. And so you start out kind of diffusely flowing, and then often these flow lines converge into these fast-moving corridors of ice called ice streams. And my research at Lamont has focused on various different aspects of this. So from the compaction of the snow in the interior, and then the fast-moving parts through the ice streams where a lot of the motion is happening, where the ice is sliding over the base. And a large part of my work is actually to do with how water is at the base of the ice, lubricating that motion. And also water is on the surface, potentially enlarging fractures on the floating ice shelves. But what I'll talk about today is actually, as Dan said, looking back into the Holocene over the last, 10, 20,000 years, and to examine how this flow pattern has changed. So this is the state today, but it hasn't been like that forever. As you know, our ice sheets, the planet had a lot more ice 20,000 years ago at the last glacial maximum. And there are reasons why we would like to understand how that's changed. And, there's many. And the two most important ones for me are, if we can reconstruct the past of the ice sheets, we can test representations of processes in models. So you say, you have a representation of some important process, like maybe the ones I've studied, water flowing over the surface. And in theory, you know how ice sheets behave in the past, and you test your models with that new representation against those past reconstructions. And the other one, obviously, is that you can also highlight important missing pieces in models. So if you see some behavior in the past, and it can really highlight some set of processes which you have been ignoring up to this point. So with that preamble about why we'd even care about reconstructing past ice sheets, I'm going to take you to West Antarctica. Now, this is East Antarctica, this is West Antarctica, this is the peninsula, and the two important sectors I'm going to keep switching between are the Ross Sea sector here. So this is the Ross Sea, and then there's the Weddell Sea here. And the Ross Sea has this big ice shelf called the Ross Ice Shelf in it, the size of France, the size of Texas, something like that. And the Weddell Sea has the Ronnie and Filchner Ice Shelf in it. So I can get all those names completely mixed up, so I'm sorry. I'm trying my hardest not to, right? This is the Weddell Sea sector. This is the Ross Sea sector. So to orient you, the biggest US base is McMurdo Research Station in the Ross Sea sector. A lot of US-based research has been in the Ross Sea sector. And then the UK base is over here in Rothera on this Adelaide Island. And a lot of UK and lots of other nations research is focused in this area. So I did my my postdoc I did my field work over here, and later I collaborated with lots of US researchers who've done work here. So that's the big picture. All right, let's zoom in on the Weddell Sea. As I said, we're interested in the past. And going into all this, we had, you know, some information, some kind of scant information about what had gone on. So this is a reconstruction by Hillenbrand back in 2014. The edge of the blue area is the edge of the ice sheet. So this is the ice sheet, and then this is the ocean. And the colour is the depth to bedding, but that's not important so much. Just keep track of this edge of the blue area. This is 20,000 years ago. We're going to click forward in time. 15,000 years ago, retreating. 10,000 years ago, retreating again. 5,000 years ago, and then finally, present day is actually this fainter line here. That's what we know is present day. So they came up with this reconstruction of what had happened during those 20,000 years. The problem was that the evidence in this area for change, it comes from terrestrial exposure dating and from marine sediments. That evidence is so scant and so contradictory that they actually had to come up with two completely contradictory reconstructions, one based on terrestrial and one based on marine evidence, so marine sediment cores and bathymetry. And so there's the picture. Like, this is 5,000 years ago based on terrestrial. This is 5,000 years ago based on marine. And they're obviously very, very different. And the implications of this are, you know, we would, for example, estimate the rate at which the lithosphere is changing its elevation in response to this history would be very different than in this case. So measurements today of like changes in gravity, for example, would be wildly off, depending on which one of these two you take. That's the kind of a situation where it's happening. Like, we could do better than this, hopefully. Okay, and then a similar kind of story in the Ross Sea, not so much contradiction necessarily, but scant evidence, you know. So we've got a progression from, what are the dates on here? Yeah, sorry, this is 20,000 years ago, and then you've got lots of question marks. The grounding line was out here, where this red line is, and gradually it retreated back to somewhere around here 5,000 years ago, and then today it's here. So the problem is, of course, these places are now covered in these large ice shelves, and ice shelves, these hundreds of meters of ice thick, and you can't easily look at the seafloor beneath them. But okay, so not very much evidence, but there was this prevailing view, at least, that the retreat was monotonic, in the sense that it was bigger somewhere out here, and sometime between the LGM, the last glacial maximum, and today, it retreated monotonically to roughly where it is today. To put it really, really simply. Now, there has been various evidence for more complex history, some of which I was involved with, but I won't go into too much detail. Basically, based on satellite imagery, on ice-penetrating radar, and so this is in the Weddell Sea, and then the Ross Sea. But no like coherent picture had really emerged, just kind of hints at something more complicated is happening. And then so I'm going to talk now about this paper, which was published in 2018 and a later one in 2019 as the start of my work on all this. So this 2018 paper had three components. One is geophysics, one is modeling, and one is like chemistry or something. No, this fish represents something specific soon. So yeah, sediment, the geochemistry of the sediment. I'm going to start with geophysics. So this is my field work, and another one of these time lapses showing our little camp. And while I'm talking, I'll describe what we were doing. So we were towing around a radar system and moving camp like regularly and taking profiles, transects of the ice sheet. And this is our radar system. Basically, you have a sled here with a well, let's start at the back. It's a very small sled at the back, which is transmitting out radio waves, basically just pulses of radio energy in all directions out of these dipole antennas, and those radio waves shoot off in all directions, and some of them go through the ice. Ice is like semi-transparent to radio waves in this frequency, bounces off whatever it sees, any contrast in dielectric properties, it bounces back, and it's received with this dipole antenna, which sits about here, and then recorded here on this system. This is a map of the area, and it's an important, and these lines show the routes we took over 2 years, and we did 5,000 kilometers of radar lines driving along at 12 kilometers an hour and just continually just taking these transects. The other thing, important part to point out about this map, this is a satellite image, a very high contrast satellite image, and it shows, and the blue line shows the grounding line, which is the boundary between grounded ice and floating ice. So here, for example, is Rutford ice stream. This is all grounded, and at this blue line, it becomes thin enough to float on the ocean, and it becomes the Weddell, it becomes the Ronnie ice shelf, and then all of this is floating ice shelf. So it starts off, 1,000, 2,000 meters thick here, the shelf, and it gets thinner and thinner and thinner. Embedded in that are these other areas, these very slow-moving things called ice rises. That was the target. That's one of our main targets of the fieldwork, and they are, and they're useful targets because this is a dynamic region. Like lots of this ice flows very fast. It's hundreds of meters a year, but these are slow-moving patches of ice which record for thousands of years changes in flow in the past. Other areas, some change in the structure of the ice, which happened 2,000 years ago, has now vectored away and become an iceberg. But in these locations, the ice is still there because it's very slow moving. That's why that was the target. So I'm going to talk about one first, the Henry Ice Rise. Yes, please.
Slowly moving because they're grounded?
Yes.
Okay.
And frozen to the bed. This is grounded and still fast because it's sliding quickly across the base. These are, and this is fast moving because it's on the ocean and there's no friction. And these are slow moving because they're thin and actually cold enough to be, there's no water at the base and they don't slide at all. So this will be moving at 10 meters a year maximum. And this immediately adjacent to it is moving at 300 meters a year. So there's a shear margin right there. So these things are like kind of nails. They're nailing the ice shelf back. Like the ice here has to flow around this really slow moving bit of ice, and it's providing a lot of stress upstream. So these things are important features. Their formation or loss controls a lot of the system. So I'm going to zoom in on one, and then the nicest one, which is Henry Ice Rise. It's a beautiful place. Like the weather was really kind to us. I have lots of fond memories of Henry Ice Rise, and it's grounded, 300 to 800 meters below sea level, and it's slow moving today. And here's that quantified a little bit. So that's the speed. We're talking meters per year. And what we did, shown in the white lines, is a bunch of radar lines. And this was reported in 2 papers, so I won't go into much of the detail. But what we found was some really interesting structures in the subsurface. Let's get the slide. And this is a radiogram. This is the surface. And then it's like a cross section through the ice. You may have probably seen these things before. And you see coherent reflectors or continuous reflectors from lots of different things. So one is the bed where the rock is in contact with the ice. And the other thing you see are these internal layers, which are very common. You see them all over the ice sheets, and they're down to changes in precipitation or changes in salinity of the precipitation, and they're called isochrones. They move with the ice as it flows. But what was much more interesting or much more surprising were these other features, these tilted, jaggedy, bright reflectors near the base of the ice, which after a lot of interpretation, we interpreted them as buried crevasses. So crevasses being fractures, which these fractures would have initially formed near vertically, and they have then since been deformed by the shear of the ice. So this is of course ice is flowing viscously, and in this location the flow is all just through vertical shear. I'll turn around like this way. So the top is going towards the right, and the bottom is frozen to the bed. So this is shear like this, and these things have been tipped over time. And one thing I forgot to say is the topography beneath this is that the highest point, this is Henry Ice Rise, this whole thing. This is the ice shelf flowing around it, off towards the ocean in the top left. The topography is highest at the northern end. That's kind of important for our interpretation. And you see all these fractures, and also the other cool thing is that there's many lines, and we had to do this all in 3D and do a proper interpretation, but these layers intersect these fractures in different places and intersect the bed in different places. Long story short, as we came up with this kind of conceptual model of what was going on, is that this is the topography beneath, and this is the floating ice shelf. at some previous time when it was actually floating above this location. The ground, it wasn't grounded like it is today, it was floating. And then it made contact for whatever reason. Maybe the ice shelf thickened, or maybe the lithosphere moved upwards, and it created a bunch of structures, fracturing, layering, which intercepts the bed, and details of this, which I won't really get to explain, are the fact that we retreated off the high point and then re-advanced, so therefore allowing for fractures to be slightly upstream of the high point. Again, all the details are in that paper. And then the top-down view is this. Well, it's pretty washed out there, I'm sorry. But that's completely floating, grounding on the high point, migration around the high point of the grounded area, and eventually the state we have today, which is grounded upstream of the high point with lots of fractures around the edges, which is exactly what we mapped out. Okay, so that was the geophysics. So then on the other side of the ice sheet, moving to the Ross Sea, in several locations in this upstream of the Ross Ice Shelf, people had been drilling through the ice over a number of decades in a number of different places, and particularly this Wizard project, big operation, and they recovered subglacial sediments. Okay, zoom in slightly in that location. So these are sediments, you know, close to the ice, close to the base of the ice in a few different places. So we've got these green dots, the places I'm going to talk about most. And these are the places we've got the sediments. Prairie ice rise is an important point for later on. And then this is Willand's grounding zone, which is right next to the ocean today. And this is the ice sheet, grounded ice sheet, flowing this direction. And then this is the shelf, the floating part. So the Sways to Sea project, which people might have heard about, is in the prairie ice, which is happening now, where they're drilling through the grounded ice, for example. Okay, so the big picture here is that people hadn't really thought to look for radiocarbon in the sediments, because the idea had been that, well, given our prevailing view of monotonic retreat, there would be no reason to expect radiocarbon in these sediments, because the half-life of radiocarbon is short in comparison to the time that this would have been last exposed to the ocean. But Reed Shearer and a few people in his team did that analysis, and they surprisingly found radiocarbon. They did this bulk radiocarbon measurement, which cannot provide you with dates. It can't tell you when it was last exposed, but it can tell you whether or not it has radiocarbon in it. And so it pointed to these places having been exposed to the global ocean during the last 30,000, 40,000 years. Because that otherwise, if it was longer than that, there wouldn't be any radiocarbon left detectable. So these places are 200 kilometers upstream of the grounding line today. You can imagine maybe there's another route for the carbon to get there through the subglacial drainage system, but there's no way that water can get from here to here given the pressure gradients. Or maybe there is raining down at the base of the ice sheet. The basal melt provides fresh radiocarbon to the system. Well, that doesn't work either, because it takes that like hundreds at least of years to. Sorry, it takes thousands of years for ice to get through the system from the surface down to the bottom. So the only explanation is that in that relatively recent past, these places were exposed to the ocean. And then that's where this fish comes in, our little friend the fish, because this is the Willand's Black grounding zone, a location where they drilled in right at that grounding line, and they put a camera down, and they saw a really teeming environment. And then this little guy swam past the camera. And obviously, it's not my field. I'm not a marine ecologist of any kind. But the point is that even when you're 600 kilometers away from the open ocean, there is an ecosystem which can explain why radiocarbon can be flushed through the system, even right here at the grounding line. So what we're saying is the grounding line was at least here and here and here. Because if that were the case, then this could be expected to be happening too. And radiocarbon would be entrained in those sediments. Okay. Yeah, that's what I've said. So I want to keep moving. So the third part of this paper was a modelling exercise to examine the potential causes for that change, for the fact the grounding line seems to have been smaller and then had been growing out again. So this is the parallel ice sheet model, actually the same model that Dan uses. And we had some representation of glacial isostatic adjustment. That's important. That's the lithosphere changing its elevation based on loading from the ice. and the surface temperature accumulation, and basic drivers from the climate are represented in simple ways, and a resolution of 15 kilometers. And there was an ensemble of simulations to explore the sensitivity of various parameters. And some of those ensemble members exhibited this behavior, which this is an example of. So this is at the LGM, basically. The ice sheet is growing towards an LGM state. This is the edge of the ice sheet, growing in both sectors. And then around 14,000 years, it retreats rapidly to a state smaller than present day, and then gradually regrows over the next several thousand years. And these ice rises form, and the ground line here readvances to roughly its state. And then that's all summarized in this plot. And this is blue line is where the ground line reached the minimum, and the green is where it regrew to. So now we made a bit of a tactical error here, because I put on the dates that this minimum corresponds to in the model, and that is the date in the model that it happened. But that is very flexible. Like, that is not a thing that that is not a prediction of the model. That happened to be the date that it happened, and I think it's interesting in the model that it's happened, and it points to some causation, which I'll talk about in a minute. But ever since this paper came out, people have always said, Kingslake et al. Say that it happened at 10,000 years. I'm like, no, we didn't really mean to say that. We never wrote it down. We said this happened in the model, and we're going to use the model in the following way, which we'll explain. But this has been a bit of a bugbear for me, because I really don't want to be claiming that, because we didn't have any evidence for the timing. And the timing is super important, as the second part of the talk will show. Okay, so why in the model does this happen? Well, this is the simulation I just showed you, the minimum state, about 10,000 years. And so what you can do, obviously, in a model is do some interesting experiments and try to work out why in the model the grounding line readvanced. So what we'll do is, at that moment when we have the minimum grounding line, we'll just turn off the glacial isostatic adjustment and not allow that to happen, and then let the model continue running. And what you find is a more retreated state. Okay, so glacial isostatic adjustment is important. We have a more retreated state instead of the readvance that we get in the other simulation. Okay, so right, back to this then. That's the reference simulation. Okay, well, what else could we do? We could say, well, we're allowed to have glacial isostatic adjustment, but these little bathymetric highs where the ice rises form, we'll just remove them. So you can't have ice rising. So what happens then? Sorry, next slide. Is that you get some readvance, but not as much as you'd expect. And then you could do the inverse, which is no glacial isostatic adjustment, but you force the grounding of the ice rises by changing the bathymetry so that it has to ground. Again, you get some readvance, but not that much. But what you need is both. In the model, I'll state that, in the model, to get readvance of a realistic magnitude, we needed glacial isostatic adjustment and these ice rises. I think it's really interesting, because the lithosphere going up on its own would cause the grounding line to advance, because you're going into shallower water, and that would just lead to just by the simple ice sheet physics, you'd expect the grounding line to be more advanced. But there's this additional thing of the ice rises, which kind of isolated high points, and they grab hold of the ice shelf and generate more back stress. And without them, in this case, we wouldn't have got the right magnitude. Okay, so that's in the model, that's why it happens. And we presented this, and then and people have worked on this, including some people in my group, ever since. And why is the big question. So one, it seems to be that people agree that the evidence points towards there having been a retreat and a readvance, but there's still disagreement on why that is. And there are these two. At the time, I presented this idea that it was a glacial isostatic adjustment. We found that in the model. It seemed like a cool idea. So this is what we think probably could have happened. And of course, the other thing that could be driving it is that some atmospheric change, some climate change drives everything. And that would involve the ocean. And this is something Dan's worked a lot on. And there's a really nice review paper, which I'm not involved with, but which is actually summarizes nicely. All right, so but eventually what people have obviously found is that the question you should be asking is really when. Because why is, if you want to get to why, you really need to know when this happened, because it makes a big difference. So ever since then, a lot of work, the really big progress on this stuff has been looking at when the Readvance happened and comparing that to records of climate to see whether those make sense to indicate climate as a driver. So back to some of the geophysics I did over on the Weddell Sea. Now this is Corf ice rise, one of the most well-studied ones we study. This is a radiogram through it. And what you see is the absence of those interesting fractures. As I say, you don't see those fractures barely anywhere else. But what you do see are these isochronal layers, which you see everywhere, all over the place. And we see them all the way through to the bed, and they have this beautiful, close to horizontal structure in these areas. But in the middle, you have this upwarping, which is called a Raymond arch. It's named after Charlie Raymond, the US glaciologist, who predicted this based on the non-linear rheology of ice, like it's a shear thinning fluid. So in places where the stress, well, shear thinning means higher stress means lower viscosity. And so the inverse is lower stress means higher viscosity. And in this place, this is the lowest stress you can get because there's barely any stress from the surface slope, because the surface slope is actually 0 here, and it's right at depth, barely anything going on. So the thing thickens up, and you get this Raymond effect, it's now called. And so that's Raymond effect is a dynamical, it affects the velocity structure. If you have the Raymond effect in place for thousands of years, the layers deform in response to that. The layers deform around this high viscosity bit predicted by the Raymond effect. So what we did was we measured the bumps. We actually measured with a different radar technique, which could be a whole different talk. We measured the vertical velocity of the ice through the column. And that was actually a first. It was the first time people had done that with radar to measure. What I mean by that is the vertical velocity of every bit of ice through the column as a profile. And so that, and what you find is the velocity here is slower than here because of the Raymond effect. So what we did was we had that velocity field and we simulated forward in time the formation of the Raymond arches and tracked that and matched them up to the observed arches. And you can see this is depth, and then this is amplitude of the arches, and the black lines are the simulated ones. And you find that if you run it to a steady state, you leave it 15,000 years or longer, you reach a steady state with much larger arches than these. But you get a really nice match between observed and modelled at about 2,500 years. So this is what people call Raymond effect dating. And so this says essentially that this flow field has been static as is for 2,500 years, although plus or minus around 1,000 given the uncertainties. So this ice rise formed, or at least it's been in its current state for 2,500 plus or minus 1,000. A really cool other bit of geophysics people were doing on this ice rise was active seismics and looking at anisotropy in the ice structure. So they have like 3 component seismometers on the surface, and the shear waves, which come back from the seismic energy of the explosion, the shear waves split along these 2 perpendicular directions. So shear wave splitting is occurring, and the stronger, the reason it's happening is because there's anisotropy in this azimuthal direction. It's anisotropic because the crystals, ice crystals, will align in a certain direction. So based on the shear wave splitting, you can come up with a map of the anisotropy, and not only can you detect anisotropy with radar and seismics, the flow of the ice itself generates anisotropy. The ice is shearing like this, and all the ice crystals are experiencing that shear, and they actually tend to align in a particular direction. Actually, the c-axes tend to end up like parallel to shear. If nothing else was happening, you just get a bunch of c-axes all stacked up like this. But this is complicated. So this is actually the state of the system today is not normal shear, it's divide flow. The ice is flowing outwards like this. So what we find is in the top half, we find ice that has just experienced, according to the anisotropy analysis, just experienced flow like this. In the bottom half, we find ice that has experienced a period of flow perpendicular to that in and out of the board, then overprinted by a period of time of divide flow. All of that, long story short, is to say that this points to before the 2,500 years, the ice flow is in this direction. So there's again like a kind of just one piece of evidence, like this. Another piece of evidence in this kind of picture is that up until 2,500 years ago, the ice was flowing up like this, and then 2,500 years ago, this was established, and it's stayed static ever since. Okay, I'm going to have to skip some details on this next one. So this is back to Henry Ice Rise, the one with all the cool, interesting stuff at the bottom. This is a paper by Martin Wearing, a postdoc in my group, now at ESA. And basically, he looked at, he mapped out all this in a lot of detail, came up with that conceptual model. But what he also did was develop a technique to date when that happened based on burial of the crevasses. And there's a whole bunch of uncertainties. It's like the biggest probably is like the initial crevasse height is a bit uncertain. It depends on the stress regime back then. The accumulation rate has uncertainties. The radar measurements themselves have a bunch of uncertainties. But we put all that into like a simple Monte Carlo thing. We came out with a time of ice rise formation of 6,000 plus or minus 2,000. So that's, we're still in the Weddell Sea. A few years earlier, I shared a postdoc office with Sarah Bradley, who was doing some modelling of the GIA, the glacial isostatic adjustment. And what they noticed was that GPS on nunataks, that on bedrock today, they're not going up as fast as you'd expect. And in fact, one of them was going down, because mostly they're going up, right? Mostly they're going up because the ice sheet used to be big and now it's small, and they're all going back up because the lithosphere is flexing back up. The mantle is flowing back into that location. Mostly these places are going up, but these ones are not going up as fast as you'd expect. And one of them is actually going down. So that was the starting point here. So she started experimenting with removing parts of the ice sheet, putting it back in various different configurations. So they're kind of relatively simplistic way, but of course the results ended up being complicated. And I'm going to have to distill it down to just say that one of the best matching ones they had was 5,000 to 6,000 years ago. A retreat started, which went on till 5,000 or 6,000 years ago. A retreat started, and then a low standing ice volume lasted for between 1,000 and 3,000 years, and then you had Readvance to the present day. And that allowed your modelled uplift rates to best match the observed GPS uplift rates /1 subsidence. Okay, so that's another piece of evidence. I'm going to summarise all this at the end, and bring it all together. Okay, so there's this other one. Another way of dating what happened is using end glacial temperatures. This is cool. This is a cool one too. So this is the state before grounding, where the ice is floating on the ocean, and this is the ground. And the basal temperature of the ice is fixed by the melting point, the pressure melting point. That actually depends on how thick the ice is, because that's the pressure. But in any case, it's set by the melting point. As soon as you ground on this bathymetric high, there's a different boundary condition now. It's the geothermal heat flux is now the boundary condition. It's a different type of boundary condition. And you tend to get cooling, especially if it's quite thin ice. So you start out at the melting point. As soon as you ground, you get cooling, gradual cooling. And people have used that. And this is a little cartoon I use in teaching just to show this. It's very idealized, but this is before at the 0 degrees. And then as soon as you ground, you start getting cooling, and that cooling slows over time. And it takes kind of thousands of years. I know that this isn't the pressure melting point, it's actually 0C, but that's just a kind of representative thing. Bob Benchadler did this at Prairie Ice Rise, did the measurements in the 80s, and showed that Prairie Ice Rise must have grounded 1,100 to about 600 years ago. Because basically it takes hundreds of years, up to thousands of years for it to cool, but we find that it hasn't cooled to its maximum extent. You're basically dating when that happened. Okay, actually this paper is great as a cool new technique, but there's no uncertainty analysis in there at all, and they use kind of set numbers for a bunch of things. And so we published a paper, Sasha Montelli and I published a paper looking at all the uncertainties and refining that data a little bit. And but the main point is the geothermal heat flux is the main source of error in this assessment. But the Suez 2C, we were one of the things we wanted to do where they're drilling through the ice shelf, through the ice sheet at the Carrarian Ice Rise, was to get a better estimate of the geothermal heat flux. They've had incredible success in that project and extracted an amazing sediment core. They don't think they've been able to get the temperatures in the sediments actually in the end, but they are going to be measuring the temperatures in the ice, which is still be useful. It wasn't the original real. The reason we wrote this paper almost was to make the point that geothermal heat flux is the most important thing. But I think that was always going to be technically a very challenging thing to do. So they've had amazing success though, like down in York. Okay, moving on. Not only have they done this at Crary, Sarah Newhouse has done this at these sites upstream as well. And I won't go into the details of this. And we had a good conversation earlier about this, and there may be a lot of uncertainty associated with these dates. But essentially, these different locations, they did the same approach. Where are my numbers? Yes, so I sort of summarize this at the end. But basically, you have retreat times of 5,000, 2,000, 1.8, 1.7, and then readvance times of 1.5, 1, and 0.8. So the idea being that you can date when you retreated past this point and then when you readvanced again, based on the evidence in this paper. All right, zooming over to, and the point, is that these are quite far inland, but we'll move back to the coastal region a little bit more to look at Ryan Venturelli's work, who of course worked with Brad on this ramp pyrolysis technique. And so there's a bunch of different numbers here, but we've got the Willens grounding zone, which is this thing which is currently right next to the ocean, ungrounded, 5 to 7.5 thousand years ago. Slightly more upstream, which is now a bit further from the ocean, that ungrounded 5 to 7,000 years ago. And so I should say, of course, these are based on radiocarbon 2, but a much more advanced technique, which I'm sure maybe you're familiar with through Brad. Like I said, you couldn't get dates from those samples, and we didn't, but this other technique is able to do this and get estimates of dates and when they were last exposed. All right, so I think that's the summary of this of Sarah Newhouse's work. So we have retreat past these locations. And actually, I've already summarized that. Let me move on from that. And I will summarize this on a plot so you'll be able to see it, don't worry. One last thing before a summary plot, which I wanted to do, because this is a grad student who worked with Jackie Osterman, and I was on this committee at Lamont, looking at Holocene to sea level. This is a really amazing piece of work, which looks at this in more of a global context. So we're talking about changes in ice sheets, so that you might expect that to be reflected in sea level changes, but they're on the kind of decimeter scale, tens of centimeters at most. And so traditionally, when you speak to the experts, they would have said that sea level records, paleo sea level records of that precision wouldn't be available. But in the last few years, that community has developed these higher precision sea level indicators, and also there's many more of them. So what Roger did was went around and digitized from the literature hundreds of new standardized sea level indicators throughout the Holocene, and he developed this Gaussian process regression approach to kind of propagate uncertainty in a sensible way through the whole process. So you've got the new relative sea level data. He's got outputs of an ice sheet model, which is actually the same model runs that I was talking about before with that animation with the grounding line moving around. We've got many, many different solid earth structures. So that's like lithosphere, flexural rigidity, and the mantle viscosity. And so then you can estimate different GIA responses, and that's all mixed in. And then also, this was a big innovation too, to take in all these thermospheric effects, estimates, the effects of the estimates into this process too. And then you go through this Gaussian process regression, and you end up with this probabilistic estimate of sea level in the Holocene. And this is the main conclusion I want to point out, and I'll zoom in on that inset. What we've got is time going from 6,000 years ago to present day. And this is the contribution of Antarctic volume to sea level. And basically anything above the 0 line is the ice sheet being smaller than it is today. And of course, as you'd expect, the uncertainties are huge. And so, but this is the advantage of this Gaussian process regression way of doing things. you can talk about the answer probabilistically. So 60% of model runs had the ice sheet, the Antarctic ice sheet, smaller than it is today, sometime during the Holocene. And you can see that by this spread. This is like the median, and then these are the different quantiles, different percentiles. So the point being, like between 4 and 1,000 years, there was a good number of these simulations which fit the data within error and predict the Antarctic ice sheet was smaller than today. Okay. Sorry for that being a whirlwind. We've got 10 minutes left, I think, ish, to summarize all this, what I think about all this, right? So what I'm going to do is plot this on a time series. Again, I've already distilled these papers down to a few numbers, right? But now I'm going to distill them further down into a time series. So 10,000 years ago to present day. Then first of all, let's do the Ross-C. And broadly speaking, blue here means an ungrounding-like event. Red means a grounding event. And green means a high standing sea level. And so what you've got is retreat. So these early on, the first thing that happens is retreat over the present coastal sites. So today, they're the most downstream, closest to the ocean. You've got retreat over the Willen's grounding zone and this subglacial lake. Later, you have retreat over the inland sites, which were further upstream. And then later, you have regrounding of those inland sites and the regrounding of prairie ice rise. And in there as well, you have this rough, from Roger Creel's work, this rough estimate of when sea level may have been highest. And so, to be honest, this is quite a coherent picture. This makes a lot of sense in a way to me. Like retreat over coastal, retreat over inland, readvance over everything. And if you compare this to this time series of, this is a temperature anomaly, the summer temperature anomaly from an ice core in West Antarctic, West Antarctic ice sheet divide, ice core. What you see is this actually corresponds to a period of, this readvance period corresponds to a cooling of a degree or so. And this retreat period, if you take this whole region, this whole time period as retreat, that corresponds to broad warming. So this really supports the idea that this was somehow climate driven, somehow warm temperatures, summer temperatures, and also annual average temperature actually, in the middle of the Holocene led to quite a large scale retreat in the ice sheet and then a readvance when it cooled. So again, by the way, not what we proposed. We said it was all driven by the glacial isostatic adjustment. And in our models, we couldn't get the climate to do this. In any case, this is what the data show. And then over in the Weddell Sea, I'm going to argue that things are much, much less clear, right? So how do we reconcile this record with either what's going on in the Ross Sea or the ice core record? So this is, we have a lot less evidence, and that's part of my point. But we have formation of the Henry ice rise, so that's in some way growth, an ice sheet growth signal. We've also got stabilization and formation of the Corf ice rise, and then the sea level record, the GIA model into comparison thing by Sarah Bradley says retreat, low stand, readvance. So, you know, we're a long way from a coherent picture. What you'd expect to see is something a little bit different. If you'd expect to see something different if it agreed with the climate record, and you'd expect to see something different if there was a clear pattern of retreat and readvance, you know, which we aren't seeing. So I think this is an open question on there. Now, of course, coming in here is Dan's work. I haven't talked about how the atmosphere warming by relatively small amount, 1 or 2 degrees, and cooling by the same amount could cause 200 kilometers of retreat and readvance. Well, this obviously, I'm sorry for the simplification of your paper, this is obviously one of the things that Dan was tackling in this paper. So how would that happen? And if and because the surface temperature of the ice is never going to go above 0, barely ever, it's not like you get more melting on the surface. Just to put, that's raising by 2 degrees is not going to push you into a regime like Greenland where you get lots of melting. So the atmosphere must be driving the ocean somehow to cause these changes. And to drastically simplify things, Dan tried warming the ocean during this period. Sorry, I'm the one doing the drastic simplification. to drastically simplify the paper, Dan made the warming in this period, and to see what happened, and you get basically a realistic retreat, to some degree. And the main point of the paper was that yes, it must have been. You can't really do this with GIA alone because a Readvance would be too early and too slow to match the data, and you can reproduce the timing if you impose this warming, which would have to be, this would have to be driven by those same, would have to be associated somehow with the climate record in the core. GIA still plays a role. I like to stand up for GIA a little bit because it controls how sensitive the ocean underneath the ice shelf is to those changes. But this is a really good example of we started out, but I'll summarize now because this is a nice example. So we started out with this idea, and we didn't have timing constraints. Well, we never said we did. And at that time, GIA or climate could have been both contenders, for the cause. And of course, it could be a mix of the two, like Dan was saying. But we didn't really know, so we proposed GIA, and amazingly, people jumped on this and came up with better estimates of the timing, which is exactly what's needed for this problem. And a whole load of people, including some of the work I did, but also some of the subglacial sediment, geochemistry stuff, came up with these estimates of timing. And at least in the Ross Sea, that really points quite heavily to the climate being the driver because it aligns in time with this. Obviously, there's no, just the alignment in time is not enough. And Dan's work and presumably more extensive modelling of the area will be able to try and find a causal link. But there seems to be strong evidence that it's the climate. And so this is still, for me, okay, but that's not the case in the Weddell Sea. The Weddell Sea we just don't have that correspondence. It's too complicated. This record is not as coherent to me. So I think the answer, the question is still widely open in the Weddell Sea, and I think there's some exciting things we could do to try and constrain that timing more and see whether GIA could have played a role, whether it's really is the climate again, but represented somehow in a very different timing. Some global changes in that Holocene climate have represented themselves in the Ross Sea very differently than in the Weddell Sea, and we don't know why. So these two, GIA versus climate. Well, why might we care? Well, if GIA is such a effective influence on ice sheet mass, then it's a kind of mitigator of future loss, and that's an idea that people have been looking at in other sectors, especially places where the mantle is very low viscosity. If you retreat, the lithosphere pops back up and mitigates some of that. So it's a negative feedback. So that might be an important one. Or conversely, if it's the atmosphere in both sectors, that's to me it suggests a lot of sensitivity, which you should probably want to understand, and we want to understand the differences and similarities between those two sectors. So those are the open questions. What made the Ross Sea sector so sensitive to warming? And that's covered nicely in this review. And then what causes these changes in the Weddell Sea sector? And that's a review paper which I was involved with Martin Seeger, summarising some of those things if you're interested. And that's where I'll leave it. Thank you very much.